Hello, and welcome to lesson 19 of this introduction to calculus with Wolfram U. The topic for this lesson is asymptotes. So let's begin with a brief overview of the lesson. So in the past, you've learned how to calculate the limits of functions at points. So for example, if I said find the limit of 3x as x approaches 2, then the answer of course is just 6. But you could also take limits at positive or negative infinity. So for example, if you said limit of 3x as x goes to infinity, the answer is infinity. And at negative infinity, just the opposite happens, you get back negative infinity. Now the nice thing is that although you might have infinite limits, the actual answer might be finite. So in this case, you have limit of 1 over x as x approaches infinity going to 0. So there are various kinds of interesting behaviors taking place at infinity, and these are the so-called end behaviors of functions, and that's the theme for this lesson, which will be used to sketch graphs eventually. So let's begin with some more motivation and talk about horizontal asymptotes. So if you look at this table over here, it's a table for 1 over x as x approaches infinity. And you see that as x becomes larger, the value of 1 over x becomes smaller. So as x approaches infinity, 1 over x gets closer and closer to 0. And hence, 0 is a horizontal asymptote of 1 over x. And you can actually check that in a plot. So you see over here, you have the graph of 1 over x, and that's the horizontal asymptote. So it's just a horizontal line to which the plot approaches as x approaches infinity. So now a more formal definition. So the limit of f of x is L as x approaches infinity if the values of f of x approach L as x becomes sufficiently large. And when you're at negative infinity, the same kind of statement holds, except you're now taking x to be sufficiently large and negative. And then a line y equal to L is a horizontal asymptote of the curve y equal to fx if the limit of f at infinity or negative infinity is L. So here's a plot for the function x squared plus 1 over x squared minus 1, and whether x approaches infinity or negative infinity, the values of y will approach 1. So roughly speaking, when x is very large, you get x squared over x squared, which is 1. Okay, so now let's talk about the opposite behavior where you do not have a finite answer at infinity. You have infinite limits at infinity. So here's a very simple example, which we saw a little earlier on as well. So when you take limit of 3x as x approaches infinity, the answer is infinity. And just the opposite happens at negative infinity. So the plot over here has no horizontal asymptotes. Okay, so now one might talk about the laws of limits at infinity just as before. So you remember that we have talked about mathematical laws that limits obey, and most of the laws also apply to limits at infinity, but you must be a bit careful. And the reason why you must be careful is that now more than ever, you could have things which are both infinity, and then when you try and cancel them, you do not get back 0. So here's an example. You have x cubed minus x, and as x approaches infinity, you get infinity minus infinity, but that's not 0, so you get back a false over here. But if you think of it as being infinity times infinity, then the answer really is infinity. Or better still, you could think of this as being x cubed as very large compared to x, so the answer is infinity. Okay, so a very important law which you can use for limits at infinity is the following. You look at the limit of 1 over x raised to r, where r is some positive rational number, and if you assume that r is positive, then this limit is always 0. And just the same thing happens at negative infinity, you get back a 0 over there as well. So for example, if you want the limit of 1 over x square as x approaches either plus or minus infinity, the answer is just 0. So this law is the basis of a lot of problem solving, which we'll see in the next few minutes. So as my first example, let's take a rational function. And if you want to limit it infinity, then notice that the highest power in the numerator and denominator is x square. So you divide by that and use a function called apart, which will break apart the expressions. And you see over here that as x approaches infinity, by the previous law, both those terms give you 0, and both those terms give you 0 as well. So the limit of the numerator is just 2. That's a 2 from here. And for the denominator, the limit is just going to be 3. That's a 3 from there. So to summarize, the limit of this rather difficult looking function is just 2/3 as x approaches infinity. Okay, so that's a rational case. And now let's take a case where you have a combination of a radical and a rational. Okay, so now that's your function f of x. And notice that the highest power is x because you got a square root of x squared roughly. So if you divide by that, then you see that the numerator will have a limit of square root of 5 as x approaches infinity, and the denominator will limit 2 as x approaches infinity. So those are the answers separately. And then if you divide them, you get the limit for the entire radical rational expression. And finally, let's take a pure radical. So here is a radical function. The problem is that as x approaches infinity, you roughly speaking get infinity minus infinity, and you cannot define that. So what we do is we work with the conjugate radical and multiply f by it. And you see over here that if you simplify it, the answer is just 4. In other words, the function is simply 4 over x plus square root of x squared plus 4. And so when x becomes very large, the denominator is much larger than the numerator, so the answer is 0 for the limit. And you can confirm that with a plot, and you see the limit approaches 0 as x approaches infinity. Okay, so how about composition? So remember that if you have a composition of f and g and you want to find a limit as x approaches a, then what you could do is you could take the limit inside the function f, so to speak, provided that f is continuous and the limit exists. So here's an example. Your function cosine of 1 over x, that's a composition. So if you look at the inner limit as x approaches infinity, then you get back 0. And then if you take the outer limit, you will get back a 1 because the cosine of 0 is 1. So here is a plot of the function, and you see that as x becomes very large, the function value approaches infinity. Okay, so now in the last 2 slides, I'll talk about 2 shortcuts for computing rational functional limits at infinity. So there are some special tricks which are well worth knowing in this area. So for example, if you have a rational function and the degree of the numerator is less than the degree of the denominator, like over here, then whether you're at plus or minus infinity, the answer is just going to be 0 because the denominator grows much more rapidly than the numerator. And on the other hand, if the degrees agree, so the degree of the numerator equals the degree of the denominator, then all that you do is you look at the leading coefficients and you get back the answer 2/7 in both the cases over here. So we covered the case of when the degree is less for the numerator than the denominator and when they are both equal. But the really difficult case is when they are both slightly different in the sense that the degree of numerator is greater than the degree of the denominator. Now, four things can happen. First of all, you have a positive expression at infinity. So you have x raised to 6 over roughly at infinity and x squared over here. And then as you approach infinity, then both these become positive infinity because the difference between the two degrees is even. If, on the other hand, you have a negative expression at infinity, negative 2/3 roughly over here and negative 2/3 roughly over there, then the answer for both the limits will be negative infinity. Now, on the other hand, if you have an odd difference for the degrees and the function is positive for large values, then you see that the degree will affect the answer in the sense that you have infinity at infinity and negative infinity at negative infinity. After all, roughly speaking, there is x raised to 9 over x raised to 6. That's x cubed. So as x becomes large, you get infinity. And as x becomes very large and negative, you get negative infinity. And finally, if the function is negative for large values of x, then you see that you get the opposite behavior. After all, when x is large, the negative sign becomes important. So you get negative infinity over here and positive infinity over there. So there are four combinations, both infinity, both negative infinity, and one of them infinity, the other one negative infinity, and then the other way around. So that's the end of this lesson. But the main point to note is that roughly the same laws hold for limits infinity as they do at individual points, but you have to be a bit more careful. There is a special rule which we saw early on for rational function limits at infinity. Sometimes you may need to use a bit of algebra to tackle cases where there are radicals, and then multiplying by conjugates might help. And in general, it's really as easy to work at infinity as it is at finite points. So with what we've learned, the next lesson will talk about sketching curves. But before you do that, do review this lesson and look at the exercise and be ready for the next lesson on sketching curves. So I'll stop over here. Thank you very much.